Antibiotics and obesity. We know of the concerns about antibiotic resistance due to overprescription. We also know that antibiotics are used ubiquitously in the raising of animals later sold for food. And we certainly are aware that there is a current crisis of obesity in the U.S. and spreading worldwide. How are these related? Let's start with obesity. So how common is obesity in the U.S.? In this nationally representative study of U.S. children and adolescents aged 2 to 19 years published in JAMA in 2016, the prevalence of obesity in 2011 to 2014 was 17%, and extreme obesity was at 5.8%. And for adults, also published in JAMA in 2016, there was another study entitled Trends in Obesity Among Adults in the United States, 2005 to 2014. The prevalence of obesity in 2013-14 was unbelievably 35% among men and 40% among women. Obesity equals a body mass index equal to or greater than 30, and Class 3 obesity equals a BMI of equal to or greater than 40. Class 3 obesity was found in 5.5% for men and 9.9% for women. So why is this important? Diabetes is a health crisis in the United States, and the single most significant risk factor for diabetes is obesity. We know that obesity is largely due to an imbalance of the energy equation of number of calories taken in versus those used. However, it's clear that this is not the only component. Genetics certainly play a role, but studies have shown that the genetic factor only accounts for about 6 to 11% of obesity. Other factors may be the social environment, in that accessibility to high-quality food and safe environments for physical activity can determine eventual obesity. Recently, the focus has shifted to a fourth factor, antibiotics. Let's look at the frequency of use in infants and children first. 33 to 39% of newborn infants are exposed to antibiotics via the mother during delivery. More than 5% of neonates have been reported to receive antibiotics. By the time the average child is 2 years old, he or she has already received close to 3 courses of antibiotics, most commonly for inner ear and upper respiratory tract infections. By age 10, the typical child has had 10 courses of antibiotics. As we will see, this exposure to antibiotics may influence gut bacteria and colonization. Other considerations involving the development of bacterial balance in the gut include cesarean delivery, breastfeeding, and that relationship to antibiotic use during pregnancy. Vaginally born infants acquire microbes as part of vaginal exposure, whereas infants born by cesarean section delivery do not. As a result, substantial differences in gut microbiota between infants born by cesarean section compared to through the vaginal route have been reported in early infancy. Breastfeeding, on the other hand, may help protect children from obesity. One theory that's been proposed is that breastfeeding helps promote a healthy balance of gut bacteria, though this depends on the mother's health, including whether she's obese. A study in 2016 in JAMA Pediatrics found that breastfeeding was less likely to protect a child from becoming overweight if the child was given antibiotics when they were very young, or if the mother took antibiotics while she was breastfeeding. Over a 12-year period, children who took antibiotics, especially broad-spectrum antibiotics, at least 4 times before age 2, had a higher risk of becoming obese by age 5. Even a single 7-day course of clindamycin has been reported to induce gut microbiota changes detectable 2 years after exposure in healthy volunteers, and women who took antibiotics during their 2nd and 3rd trimesters of pregnancy had a significantly higher risk of having obese children. So a summary of the studies to date. There are strong epidemiological studies that suggest that antibiotic exposure in infancy is associated with a higher body mass index, as well as an increased risk of overweight and obesity later in childhood. Also, data from these reports suggest that exposure to antibiotics appears to be particularly detrimental during the first 6 months of life, and this appears to be dose-dependent. And in 2013, in the International Journal of Obesity, in a study of over 1,000 children, the researchers conclude, quote, exposure to antibiotics during the first 6 months of life is associated with consistent increases in body mass from 10 to 38 months. Exposures later in infancy, 6 to 14 months or 15 to 23 months, are not consistently associated with increased body mass, unquote. So one obvious question is, do all antibiotics have the same effect? The effect depends on antibiotic type. Are they gram-positive or gram-negative specific? Are they narrow-spectrum or broad-spectrum? And on its route of administration, intravenous or oral. For example, compared to amoxicillin, an antibiotic treating more gram-negative infections, intravenous vancomycin for gram-positive bacteria has been demonstrated to be associated with the development of adult obesity as well as in the modulation of intestinal microbiota diversity, bile acid metabolism, and peripheral insulin sensitivity. For adults, the question is obesity related to short-term or long-term antibiotic use, or can it be due to constant low-dose exposure through diet? This topic is addressed in Obesity in the United States, Dysbiosis from Exposure to Low-Dose Antibiotics, published in Frontiers in Public Health in 2013. The sale of antibiotics for use in pigs, chickens, cows, and seafood rose 20% between 2009 and 2013. About 32.6 million pounds of antibiotics are used, given at low doses to promote faster growth or prevent disease in crowded livestock pens. Obesity increased very slowly until the middle of the 1970s, then exploded. Well, what changed? The levels of antibiotics in our food and water, and the amount of processed food products. It's estimated that the use of antibiotics in food animals will increase 67% by the year 2030. In China, India, Brazil, and Russia, antibiotic use is expected to increase 99%, far more than those countries' population's growth. So where are the sources? Pork has the most antibiotics, then chicken, then beef, according to research in the Proceedings of the National Academy of Sciences. However, farmed shrimp and fish, even farmed salmon, have high levels of antibiotics because the drugs are needed to prevent disease in the farming pens. Even organic vegetables have antibiotics in them because about 75% of antibiotics fed to livestock are excreted out and in the manure used to fertilize fields. A key term in the discussion of our gut populations of bacteria is microbiome. Soon after a draft of the human genome had been completed, Letterberg coined the term microbiome to represent, quote, the microbes that share our body space and that inhabit our skin, our mucous membranes, and our gut, unquote. The obvious question, can we influence the microbiome, making it rich in diversity and favoring the bacteria that don't promote obesity and do promote colonic health? It appears so. Prebiotics and probiotics are how. But what do these actually refer to, and how are prebiotics and probiotics helpful? You will often hear that some 90% of the bacteria in the gut fall into two groups or phylum, Bacteroidetes and Firmicutes. Early evidence was from rodent studies. Obese mice had a preponderance of Firmicutes, while lean mice had a greater proportion of Bacteroidetes. Note that in humans, research has indicated that the intestinal microbiota associated with obesity has been shown to increase intestinal energy uptake from the diet and its storage in the host, primarily in the colon. This is particularly true of Firmicutes, and we know that changes in gut microbiota composition precede the development of overweight and obesity and may be observed already in early infancy. Studies that explain the results using bacteriophyla need to be read carefully because of the complexity of naming bacteria. Remember the taxonomy of bacterial categorization. We have phylum, class, order, family, genus, and species. Let's look at some observed changes based on diet. A Western diet has in some studies been shown to increase the relative abundance of Firmicutes due to an increase in the class of Mollicules at the expense of Bacteroidetes, including an enrichment in genes enabling energy increases from the diet. In one study, 12 obese subjects had lower Bacteroidetes and more Firmicutes in their distal gut than did lean control subjects. After randomization to either carbohydrate-restricted or fat-restricted diets for 52 weeks, the proportion of Bacteroidetes increased over time, mirroring reductions in host weight, but not dietary changes. Again, it isn't simple. Complicating or confounding issues are being obese may affect the bacterial balance in the gut. When obese people lose weight, their proportion of Bacteroidetes increases relative to Firmicutes. Genetic factors may also play a role in determining the balance between these two bacterial groups. The effects of antibiotics, in particular broad-spectrum antibiotics, leads to changes in the balance of gut microbes. Infection itself may alter the gut microbe balance. So, how might we affect the balance in the microbiome to the benefit of the human host? Let's start with prebiotics. What are they? They are undigested or incompletely digested carbohydrates, such as resistant starch and dietary fiber. Although the colon used to be thought of as a storage site of waste and water absorption, it's become clear that the colon is highly significant in its ability to create important metabolites and also to absorb important nutritional factors influencing local health and overall body energy sources. Here's how prebiotics play a role. Although the local environment provides mucins, desquamated epithelial cells, and digestive enzymes as additional substrates to intestinal bacteria, the majority of substrates required by intestinal bacteria for their growth is provided from diet. Important dietary substrates for gut bacteria include undigested or incompletely digested carbohydrates such as resistant starch and dietary fiber, prebiotics. The latter includes a large variety of carbohydrate polymers typically found in dietary plants. These are fermented to short-chain fatty acids. This enables the body to take advantage of indigestible carbohydrates that otherwise would be excreted unused. How are these non-digestible carbohydrates, such as dietary fiber, utilized? As stated, they're fermented into short-chain fatty acids that then produce butyrates, acetates, and propionates. So why is this important? A diet rich in fermentable but non-digestible carbohydrates has been shown to alleviate obesity in children via modulation of the gut microbiota. Specifically, butyrate is important and has been determined to be an immune regulator. Butyrate, one of the short-chain fatty acids, regulates intestinal macrophage function via histone deacetylase inhibition, decreasing inflammation. It signals that the levels of good bacteria creating butyrate are within the desired range. It's been proposed that low levels, due to low fiber intake and a resultant change in the microbiome, allows chronic inflammation and perhaps chronic bowel diseases. Low levels of butyrate is interpreted as bad bacteria versus low fiber. And yet another common nutritional term, phytochemicals, aka antioxidants, flavonoids, flavones, isoflavones, and catechins. Phytochemicals are non-nutritive plant chemicals that protect the host plant but may also protect humans against disease. There are more than 1,000 known phytochemicals. Some of the well-known phytochemicals include lycopene in tomatoes, isoflavones in soy, and flavonoids in fruit, part of a larger group called polyphenols. Dietary polyphenols are natural compounds occurring in plants, including foods such as fruits, vegetables, cereals, tea, coffee, and wine. Polyphenols are generally classified into flavonoids and non-flavonoids. Depending on their degree of structural complexity and polymerization, 5 to 10% of these compounds may be readily absorbed in the small intestine, but the majority, 90 to 95%, reach the colon, where colonic bacteria act enzymatically on the remaining unabsorbed polyphenols. Through both the phenolic substrates supplied to the gut bacteria and the aromatic metabolites produced, these metabolites may modulate or cause fluctuations in the composition of the microflora populations through selective prebiotic effects and antimicrobial activities against gut pathologic bacteria. Now on to probiotics. What are these? Generally, it is the ingestion of beneficial or friendly bacteria in an effort to tip the balance toward health. 20% of antibiotic-treated children develop diarrhea. Antibiotic-associated diarrhea results from an imbalance in the colonic microbiota caused by antibiotic therapy. Microbiota alteration changes carbohydrate metabolism with decreased short-chain fatty acid absorption and osmotic diarrhea as a result. A Cochrane review in 2015 concluded that the evidence gathered suggested a protective effect of some probiotics in this condition in children. In adults, some probiotics showed a beneficial role in reducing the occurrence of antibiotic-associated diarrhea. Treatment with probiotic formulations, including L. rhamnosus, may reduce the risk of antibiotic-associated diarrhea, improve stool consistency during antibiotic therapy, and enhance the immune response after vaccination. The potential efficacy of probiotic prevention of antibiotic-associated diarrhea is dependent on the probiotic strain used and on the dosage. Obviously, the connection between antibiotics and obesity and the protection and cultivation of a rich microbiome is more complex than this brief introduction allows. So, how do we approach this topic, in particular with the concept of increasing the richness of our microbiome, regardless of underlying causes of dysbiosis? We'll be aware and sensitive to the fact that antibiotics do influence the gut microbiome. However, the effects are specific and contextual. Antibiotics given in the first 6 months are more influential. Broad spectrums are more influential than narrow spectrum. Changes seem to normalize over 2 months to as much as 2 years. Exposure of the mother to antibiotics exposes the fetus, which may influence the beneficial effects of breastfeeding. In adults, antibiotics may result in overgrowth of C. difficile. Chronic antibiotic exposure through food may alter the microbiome. So how do we affect the microbiome? Nutritional strategies include increasing fiber with subsequent production of short-chain fatty acids and butyrate, which in turn may influence the microbiome. The hope is that this will prevent or normalize dysbiosis, which may lead to inflammation or inflammation leading to dysbiosis and then obesity. Increases in polyphenols may affect the microbiome through both the phenolic substrates supplied to the gut bacteria and aromatic metabolites. And finally, probiotics may also allow a strategic approach to supplying good bacteria.